This is my first video on simple harmonic motion, and this is the first video entitled Basic SHM Proofs. So I'm just going to be starting off the topic, and there'll be about 4 to 5 videos on this topic in the coming time. So the first formula you need to understand is the time period is the inverse of the frequency, and we all know what the wave anatomy is. Wave anatomy, the two-dimensional representation of so that's the direction of propagation of energy, and that's a function of time, as a function of time. And so this is the amplitude, that's the displacement, a random point, and that's the wavelength, and that's the frequency is number of cycles per second. So, and that's the one time period for one wave cycle. So time period is inverse of the frequency. And then we know that rate of a, so in simple harmonic motion, it's all about the springs, and we know springs are made of metal. Metal has mass. Mass has is exerting a weight under it, and the Earth is exerting a weight on the mass, on the spring, as a function of gravitational constant. So that'll be mg, and then but the extension, the energy of extension would be ke or kx, and when you equalize the two, you get the basis for this formula, the time period, 2 pi, because it's obviously it's a radiant phenomenon, so it'll be 2 pi every single time, k over m, or 2 pi L over G. So that's the proof for that. So if we start off from there, we equalize the two forms of force, and we get the basis for the derivative of the radian derivative of time period. And so that's that. And we can also get the formula of acceleration. I think this marker is dying, so bear with me please. So we can also derive the formula of acceleration. So that'll be F mg subscript mg equals fkx. So that'll be ma kx, and that'll be k equals k over mx. So that'll be minus because k is always going back. So when you extend it, it's always bouncing back due to elastic deformation. Now when it goes plastic, it wouldn't be able to, and it would be stuck in the configuration where it's been deformed. So that's that. This is the first basics of understanding the calculational foundation of SHM. Now, if we were to derive a formula for velocity, so we've got acceleration here. Now, if we wanted to derive a formula for velocity, the radial velocity of a spring, that would be, I mean, we know that simple harmonic motion is where the spring is going back to its original point of oscillation, 0 points. But that's not for now. We're not going to get to it now. We'll start with velocity. So velocity, we know velocity vector is small change in distance over small change in time, dx over dt. Not partial derivative, but you know. And then if we add a constant to it, we will get x naught. X naught is this one. This could be x naught. and x naught 2 pi f squared cos t. So how would we reach it? Now we would go from here to here, but how? How? I'll show you how. It'll be the first step would be x naught, which is this sine, I think, yeah, sine 2 pi ft. Now this t is not the same as that t. This t is the time passed. This is not the time for one cycle of oscillation. So if we derive it, if we take the derivative, it would be x, if we invert it to cosine, and we take the derivative, we have to, then it would be x naught cos 2 pi f t, and it'll be d over dt omega t. So t cancels, and we get omega squared. So we get vector v, we get omega x naught cos omega t. We get this. So once we get this, we'll be able to simplify it over there. So that'll be this, the answer. That's the velocity of a particle in simple harmonic motion on a spring. So if you've got a spring and you are extending it, so this is the length and that's the extension, and you are extending it, it's oscillating back and forth. This is the formula that'll cater to. So this formula will cater to calculating the velocity. Once you know the frequency and the displacement will be roundabout extension, so then you'll be able to find out the velocity. Now the springs, what you need to know about springs, just a thought, they can be in parallel and they can also be in series. So they can be in parallel or series, and that's what you need to understand. So they would have different equations, and that's for undergraduate level. But for now, we started off all the way from the anatomy of the wave, where we quickly described the wavelength frequency, because we know that C equals F lambda for transverse wave propagation. This is the lambda, F lambda, and we could also write lambda over T. We could also, and so this is how we calculate the time period. Time period is time taken over one wave cycle. One wave cycle is 1 lambda. This is the amplitude. So, and then this is a displacement. Displacement is basically any point. It could be amplitude or it could be any other point at node, antinode, and then you equate these two forms of rate together to get the radian time period derivative. We can either use this or this, and then once we do that, we're able to get some form of semblance of formulaic derivative or acceleration of simple harmonic motion. Always put a little SHM here to specify it, and then we did the derivative for how we start off from here how we start off from here and go all the way to here. So I went from 1, 2, 3, 4, and bingo, 5. So dx over dk sine p. We do take the derivative, cancel the t out, we're left with double omega squared. We simplify the omega squared, and then we get this. So I use this normally people use this version, but I use this because it compiles all the values in one go, and it's easier for me to calculate it. And so it'll be in rads per second. Rads per second. Beautiful. So, and then these are springs in series and parallel. So that'll be in series and parallel, and series and parallel. And that's that. And yeah, I hope you learned the basics of SHM today. The next formula I'd like to take you through would be, sorry, let me collect my markers. Next one I'll be talking about is how to derive t equals the acceleration of minus omega squared x. So I'll be deriving the proof for that's basically what it's saying is 2 pi f squared r, yes, and then that's I'm just expanding it back, reverse expansion. That'll be 4 pi squared f squared r. And basically, if I were to calculate the simple harmonic motion of a spring, I'd need to know this and this, and so that'll be, I mean, it could be, I mean, there are quite a lot of phenomena that are considered to be in simple harmonic motion. It's not just the springs, to be honest. So this is how it would look like. Now, this is one simple form of it, but how would we reach from there to here? So we do A equals acceleration equals d omega displacement. So d omega displacement, and use the same formula we got for the velocity, and then take a time derivative of it divided by time. Basically, that's what I'm doing here. So d over dt, and then we cancel the time out. So that'll be, now we've got 2 omegas, so d over dt, that's that. Then we've got x naught omega squared and cos t. Now it shouldn't be written like this. It ought to be d over dt derivative. It ought to be written x naught cos omega squared t. This is not the right way to write it, because it would then be a cos of the time. You can't take a cos of the time. You have to take a cos of omega. So this is incorrect. So this is how you write it. And I would take the sine derivative of it afterwards, and that would become, so I'd take the omega x displacement out here, and then reverse sine d over dt, and then t, so that it would cancel out. We would be left with minus sine omega t omega, and that would be and then acceleration. Sorry, there's nothing written here, so you can copy it. Bear with me, please. Alright, so that'll be... So now ponder over it, and now I'm going to simplify it further. Brilliant, brilliant. So minus sine omega to omega. Notice how it got cancelled and it got converted into omega. And then that'll be and followed by now I want you to ponder over it. So look how I've gone from that stage. Sorry, the markers are coming in the way. So how I've gone from proof for SHM acceleration, and so I did a simplification of it. So I did a simplification of it, and then A equals d omega cos omega t. Then we did dt. So I jumped over from here to here. So that was a wrong. I wanted to display that this is not how you write it. So that's why that step is incorrect. And then so you separate the d over dt here. Got the x, you've got the cos omega squared t. And you take the minus sign and derivative, take the derivative again. And then we're heading for the final stop. And that'll be omega. So this goes in here. And when it goes in here, the negative sign disappears and the negative sign goes out and comes here. So that'll be that's that. And so A equals and after that, the final closing statement would be so x naught sine omega t squared and it'll be because that's why. So I hope you're able to understand this. The negative sign, the negative sign, the negative sign goes out here, and then so this 1 omega comes out here, becomes squared. This x goes in here, this multiplies here, and then that's that. So now let's revise it. So this eventually would be minus 4 pi squared f squared r equals 4 pi and so that's the sinusoidal component, and that's the oscillatory component. So that's the sinusoidal, so that's the oscillatory component, and that's the sinusoidal component. That's that. And sorry about the thing, the orange colour is not coming out well, but it's I've used up a thickness because it was, the orange nib was quite thick. So yeah, that's how it goes. Start off from here. We had to reach this part. So the linear version, the oscillatory is the oscillatory version was this one, and then we had to add the sinusoidal component to it to make it this. So this would be this would become an actuality. Sorry, this doesn't mean anything. And yes, please. There we go. Yeah. So that would be then this, and then this would be that. That's the full equation. That's the full equation, and minus 4 pi squared f squared x naught sine 2 pi ft. There we go. That's that. So we had to do all of that to get to this. And so the first one is, so that's the proof, the title. Proof for simple harmonic motion, acceleration. Right, I couldn't write acceleration, just put the A. And then we know that in simple terms it's minus omega squared r, the radius of oscillation, which means this, which means this, which means this. So that's the oscillatory component, up and down, but we had to add the sinusoidal component as well. So this and this, because this kind of motion added to this kind of motion equals this kind of motion. So up and down and circular equals this kind of motion. So that's, and you'll find a lot of examples of SHM in engineering and engines. And so we start off from this. I give you the template. A equals d of dt w x, omega x naught cos omega t, and then separate the d of dt out. And I showed you the way of not doing it, so that's the misconception part. I addressed the misconception, and then I told you how to write it this way: x naught cos omega squared t. Then I began to spread it out, simplify it, and then I started using the black ink too. Now that's just, it was that, and then I told you that it has to be an oscillatory and sinusoidal component, and that's how the formula would actually look like. So this is how things are. Just need to flip. Now let's just take an overview. This is the overview. That's that, that's that. Let's put a black arrow here. This to this. This to this. This to this. And that's it. This is how we reach here. And then these are just sidelined hashtag explanations. So and now we'll do a proof for the total energy in simple harmonic motion system. Bear with me, please. Now we all know that in a sinusoidal system, in potential energy, kinetic energy, they have an inverse sinusoidal relationship. So in my previous video, I showed you the graph of total energy equals potential energy plus kinetic energy. So we know that this is the case, and if we take F equals half kx squared to be the strain energy, that'll be, and that's that. And then if we take the potential energy as and if we take kinetic energy as half kx squared again, and we would then get 0 plus half kx squared equals half. Half's going to get cancelled out, so don't worry about the half. And so we cut the half out, and we get left with k, not x squared, m x squared plus k x squared. We can take so that gets cancelled out, I guess. So that's that. And now we take the mass over the other side. Sorry, it's not a knot. And that'll be so that's basically V. That's that, and yeah. So the complete derivative of how to get the total energy. So the total energy of simple harmonic system is this. And to derive the velocity out of it, it shall be this way. And if we separate the variables and integrate them, we can then carry on with the substitution to find out that it'll lead us to sine naught over x naught equals k over m plus a constant. And that would then eventually lead us to displacement formula. So we're working backwards. And we've already done acceleration, so there's no need for that, but we've just wanted to show how you could reverse engineer the formula for velocity from the total energy. And it's important to know what the formula I've used for PE, KE, and F. That's the strain energy, and that's the potential energy of a spring, kinetic energy of a spring, and yeah. And the rest is pretty much the same, to be honest. So in angular kinematics, so in angular motion, you have to worry about acceleration, velocity, displacement, and there are sinusoidal formulas for it, just like in AC theory. The formula for current is current equals peak current sine 2 pi f t, and voltage is peak voltage sine 2 pi ft, because in real life most phenomena are sinusoidal. It's not linear. Nothing's linear in real life. In real life, it's very imperfect and very non-linear. And most phenomena in the national grid and all of these are non-linear. So non-linear is I mean, kinematics and dynamics, linear kinematics and dynamics are very ideal. So you'll have to, in angular motion, you'll have to come up with sinusoidal formulaic derivations for acceleration, velocity, and displacements. So we started off from this. Please take a screenshot. And then we moved on all the way to measuring. So this is the spring constant. That's the mass of the spring. That's the amplitude, and that's the any given displacement. So and that's the radius of oscillation, 2 pi ft, mass of the spring, and that's how things are. Please take a screenshot of this. So I've decided to write it on a smaller piece of paper for you. It took me about 10 minutes. So this is the interaction and relationship of potential energy, kinetic energy exchange in oscillating systems, i.e. SHM. The energy in a stretched spring is potential energy, and that's the formula for it, half kx squared. And the potential energy can also be found as work done, average force on spring times the the extension, and that'll be 0 plus F over 2. And times x, so f over 2 times x, half x squared, kx over 2, and the kinetic energy of the spring would be half m omega squared r omega squared x squared. So half m omega squared x squared, and then when you add the two, you get kx squared mv squared over 2, cancel out the half, take a screenshot please, and that'll be this one, sine omega t. Because it has to be sinusoidal, you have to shove in the sinusoidal elements to the because there are three. I wanted to explain this. There are 3 types of oscillations. The 3 types. Sorry, bear with me. So there's vibratory, oscillatory, vibrational, translational, and rotational. So vibrational, translational, rotational. So vibrational is this one, up and down. Oscillation, translational is this one, and rotational is axial. It's also known as axial. So that's axial. So it's like, hang on, let me get the ball. So vibration, if a particle was oscillating, it'll be like this. Translational would be like xy xy xy. Sorry, x x x x x x x minus x plus x minus x plus, and then vibrational would be y plus y minus y plus y minus, and it would be translation rotary rotational would be mapping the z-axis at a 360 degrees. So mapping the z-axis at 360 degrees, and that'll be, let me show you. So if you had Cartesian coordinates 3D axis, so up and down would be translational, yeah, vibrational, and then this would be translational, and then z would be z, so that would be rotational. VTR, 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 vibrational, translational, rotational. That's that. Thank you very much. That's good. Alright, coming back to this. Sorry, now, as I wrote just here, total energy would be m squared over m squared, m omega squared r over 2. So you add it at the you add the 2 kepe at the juxtapose the sinusoidal component, and then you add the sinusoidal component here, sine squared omega t sine squared cos squared omega t, because one will be sine axis, the other will be cosine axis, and then you add them, and that'll be constant. This part will be constant, and then you bring it down. And so you need to practice this compilation of proofs and memorize them in a sequential manner, this one and this one. So these proofs are specific to SHM, but can be applied to all levels from AS to postgraduate level. So I'm going to put this here. You could take a screenshot for 10. I'm going to put this here. You could take a screenshot, print it out, and then yeah, I hope you took the screenshot. So that's how things are. And so it was just a basic understanding of, now I'm going to draw some. Thank you very much for tuning in. That concludes the video. If you've got any comments or questions, post them down below. Please like, share, and subscribe the video. Even if you don't love the subjects, please share it on your Instagram and let other people benefit from it. Thank you very much. Cheers. Take care. Bye now.